Lastly, let us consider the same RLC circuit with the same initial conditions. This time we just changed our resistance to 400 ohms. We will repeat the same solution process we have done thus far in examples 1 and 2. We know our current initially running through our inductor is 30 milliamps, and we know our current running through our resistor is now 30 milliamps due to the change of our resistance. Thus, the current running through our capacitor is minus 60 milliamps, i.e. our device is discharging. For us to construct a solution, we need to determine the roots of our equation. Alpha, which is equal to 1 per 2 RC, is equal to 6,250 seconds inverse. Omega naught is equal to 10,000 seconds inverse. And when we calculate lambda, we have minus 6,250 plus or minus 1,250i times the square root of 39 second inverse. Since we have complex roots, we have to use Euler's equation. That is, v of t is equal to a1 e to minus alpha t cosine omega dt plus a2 e to minus alpha t sine omega dt. We define omega d as the square root of omega naught squared minus alpha squared. At time t is equal to 0, the voltage across our system is 12 volts. Thus, when we populate t is equal to 0 into our previous expression for voltage as a function of time, a1 is equal to 12 volts. We know that the time rate of change of voltage within our system is equal to our current running through our capacitor times our capacitance, and we have dV dt is equal to minus 300,000 volts per second. When we differentiate our voltage with respect to time, we have e to minus alpha t times the entire quantity, omega d a2 minus alpha a1 times cosine omega dt minus omega d a1 plus alpha a2 times sine omega dt. Or this implies that omega d a2 minus alpha a2 is equal to minus 300,000. With two equations and two unknowns, we solve for a1 to be 12 volts and a2 is equal to minus 60 times the square root of 3 per 13. Thus, our solution takes the final form. Our voltage as a function of time is equal to e to minus 6,250t times the quantity 12 times cosine 1,250 times the square root of 39t minus 60 times the square root of 3 per 13 sine 1,250 square root of 39t. And since omega naught squared is greater than alpha squared, we have an underdamped response. If we plot our solution, we go from 12 volts, we approach about minus 9 volts around 0.15 milliseconds, where then our voltage increases and overshoots our steady state value, reaching about 1 volt around 0.5 milliseconds. Then our solution decays to our steady state response. An underdamped response typically has some oscillation about the steady state solution.